Welcome to our comprehensive exploration of containerization in DevOps. Containerization has revolutionized how we deploy and manage applications, making it a crucial skill for any DevOps professional. In this session, we'll dive deep into practical examples of containerization using Docker, examining various use cases from simple Python applications to complex multi-container deployments. We'll explore best practices, common pitfalls, and real-world scenarios that you're likely to encounter in your DevOps journey. By the end of this module, you'll have a solid understanding of how to containerize different types of applications and manage them effectively in production environments. Let's start with a fundamental example of containerizing a Python application. The Docker file we're examining is a perfect starting point for understanding container basics. The choice of Python 3.9 as our base image is deliberate. It provides a stable foundation while maintaining compatibility with most modern Python packages. When working with Python applications in containers, there are several critical considerations to keep in mind. First, always use specific version tags for your base images rather than latest to ensure reproducibility. The working directory setup under /app is a common convention that helps maintain a clean container structure. One crucial practice I've learned from production deployments is to copy your requirements.txt file separately before the application code. This leverages Docker's layer caching effectively. If your dependencies haven't changed, Docker will use the cached layer, significantly speeding up your builds. The final command using Python to run app.py is straightforward, but in production, you might want to consider using a production-grade WSGI server like Unicorn instead of the basic Python interpreter. Let's examine the key components of our Python application, Docker file, in detail. Each instruction serves a specific purpose in creating a production-ready container. The from instructions choice of Python 3.9 is strategic. It provides a good balance between stability and modern features. When setting the working directory with workdir, we're following a container best practice of isolating our application files. The separate copy commands for requirements.txt and application code aren't just for clarity, they optimize Docker's layer caching mechanism. If your requirements don't change, Docker reuses the cached layer, significantly speeding up builds. A common pitfall to avoid is using pip without the -no cache dir flag when installing requirements in production containers. This flag can reduce your image size significantly. Also, consider implementing virtual environments within your container if you need to manage complex dependency scenarios. Moving on to our Nginx example, we're introducing a more sophisticated pattern, multi-stage builds. This approach is particularly valuable for JavaScript applications where we need different environments for building and serving the application. The first stage uses Node.js 14 for building our application, while the second stage uses a lean Nginx image for serving the content. This separation is crucial for security and performance. By using multi-stage builds, we typically see image size reductions of 50% or more compared to single-stage builds. The -from equals builder syntax is particularly powerful, allowing us to cherry-pick only the necessary artifacts from our build stage. When working with Nginx in production, consider customizing the engine.x.conference file for your specific needs, such as enabling zip compression or adjusting worker processes. The command to run Nginx with daemon off ensures proper container lifecycle management, a critical detail that's often overlooked but essential for proper operation in orchestrated environments like Kubernetes. The Nginx Docker file implementation showcases several advanced Docker patterns. The multi-stage build approach is particularly powerful for front-end applications. In the first stage, we're using Node.js to build our application, which includes all the development dependencies and build tools. However, these aren't needed in production. The second stage, using Nginx, creates a much smaller and more secure production image. When copying the built files to the Nginx HTML directory, ensure proper file permissions are maintained. In production environments, consider customizing the NIC's configuration for better performance, enabling zip compression, adjusting worker processes, and implementing proper caching headers. The expose instruction is purely documentary. Remember to explicitly publish ports when running the container. The concept of lighter base images is fundamental to efficient containerization. Using smaller base images isn't just about saving space, it's about security, performance, and maintainability. When working with production containers, every megabyte matters. Smaller images mean faster deployments, reduced network bandwidth usage, and lower storage costs. From a security perspective, smaller images present a reduced attack surface. Consider using Alpine-based images when possible, which can reduce image sizes from hundreds of megabytes to tens of megabytes. However, be cautious. While Alpine images are smaller, they use muscle libc instead of glibc, which can cause compatibility issues with some applications. Always test thoroughly when switching to lighter base images. Let's delve deeper into the advantages of multi-stage builds and lighter base images. The isolation of build artifacts is particularly crucial for security. In real-world scenarios, build environments often contain sensitive information like API keys or certificates that shouldn't make it to the production image. Multi-stage builds provide a clean separation, ensuring these secrets don't leak into your final image. Build optimization through layer caching is another critical advantage. In CI/CD pipelines, efficient caching can reduce build times from minutes to seconds. When implementing multi-stage builds, organize your stages to maximize cache utilization. Place the most stable, least changing operations first. For example, in a typical Node.js application, install production dependencies first, then development dependencies, and finally copy your application code. This ensures that changes to your application code don't invalidate the cache dependency layers. Adding database connectivity to containerized applications introduces important considerations around configuration management and security. This Docker file demonstrates the use of environment variables for database configuration, a crucial practice in the 12-factor app methodology. However, there are several production considerations to keep in mind. Never hardcode sensitive credentials in your Docker file. Instead, use environment variables or, better yet, secrets management solutions like HashiCorp Vault or AWS Secrets Manager. When working with database connections, always implement connection pooling and proper error handling. Consider adding health checks to ensure your application can properly connect to the database before being marked as ready. The expose instruction is documentation. It doesn't actually publish the port. In production, you'll need to explicitly publish ports using the -p flag or Docker Compose configuration. This Docker file demonstrates critical patterns for database-connected applications. The environment variables pattern shown here follows the 12-factor app methodology, but there are important considerations for production use. Never store sensitive credentials in environment variables directly in the Docker file. Instead, use runtime injection through orchestration platforms or secrets management systems. The installation of dependencies before copying application code optimizes rebuild times through Docker's layer caching. When connecting to databases, implement proper connection pooling and retry mechanisms to handle temporary network issues. Consider adding health check instructions to ensure your application can properly connect to the database before being marked as ready. This Docker Compose configuration introduces us to running multiple application instances sharing a single database, a common production scenario. The replicas setting demonstrates basic horizontal scaling, but there are several critical considerations. First, ensure your application is stateless. Any shared state should be managed through the database or a separate caching layer like Redis. The resource limits specified here are crucial for production deployments. Without them, a single container could consume all available resources. The network configuration creates an isolated network for your services, enhancing security. When deploying multiple instances in production, consider implementing proper load balancing strategies. While Docker Compose provides basic load balancing in production environments, you might want to use solutions like HA-Proxy or cloud-native load balancers. Also, implement proper logging aggregation to track requests across multiple instances. The environment variable's configuration in this Docker Compose file demonstrates proper externalization of configuration. Each variable using the $variable_name syntax allows for flexible deployment across different environments. When implementing this in production, consider using env for development but proper secrets management for production deployments. The deployment configuration with replicas enables basic horizontal scaling, but remember to ensure your application is truly stateless before scaling. The resources section with CPU and memory limits is crucial for production deployments. Without these limits, a single container could consume all available resources. The network configuration in this Compose file creates isolated networks for your services, enhancing security through network segregation. The deploy section's replica configuration enables basic horizontal scaling, but in production environments, you'll want to implement proper load balancing and service discovery. When using replicas, ensure your application is truly stateless. Any shared state should be managed through the database or a separate caching layer. The resources section with CPU and memory limits is crucial for production deployments. Consider implementing proper monitoring and logging aggregation when running multiple instances to maintain observability across your distributed system. Understanding the distinction between Dockerfile and Docker Compose.yml is fundamental for DevOps professionals. The Dockerfile defines the container image blueprint, while Docker Compose.yml orchestrates multiple containers and their relationships. In production environments, you'll often need both, Docker files for building optimized images and Docker Compose for local development and testing. When working with these files, maintain version control and implement proper documentation. Consider using Docker Compose.override.yml for environment-specific configurations. Remember that while Docker Compose is excellent for development and testing, in production environments, you'll likely use orchestration platforms like Kubernetes or AWS ECS, which have their own configuration formats. Volume management is crucial for maintaining persistent data in containerized applications. This example demonstrates mounting an NFS volume, but there are various volume types to consider based on your needs. When working with volumes in production, implement proper backup strategies and consider using cloud-native storage solutions like AWS EBS or Azure Disk Storage. The volume configuration shown here includes important options like no-lock and soft mount options. These are crucial for handling network interruptions gracefully. Always implement proper permissions and ownership for mounted volumes to prevent access issues. In production environments, consider using volume plugins that integrate with your cloud provider's storage services. Remember to monitor volume usage and implement proper cleanup strategies to prevent storage leaks. The volume configuration shown here demonstrates proper persistent storage management for containerized applications. When using NFS volumes, pay careful attention to the mount options. No-lock and soft mounts are crucial for handling network interruptions gracefully. In production environments, consider using cloud provider-specific storage solutions that offer better performance and reliability. Implement proper backup strategies for your volumes and monitor storage usage to prevent capacity issues. When mounting volumes, ensure proper permissions and ownership to prevent access issues. Consider implementing volume cleanup policies to prevent storage leaks and unnecessary costs. The build process is your first step in deploying containerized applications. When building images, always use explicit tags rather than relying on the latest tag. Implement proper versioning strategies. Consider using Git commits or semantic versioning for your tags. In CI/CD pipelines, You might want to include additional build arguments for version information or build time configurations. Always verify the build context to ensure you're not including unnecessary files that could bloat your image. Consider implementing multi-arch builds if you need to support different CPU architectures. Remember to scan your images for vulnerabilities using tools like Snike or Aqua Security before deploying to production. Proper image tagging is crucial for maintaining order in your container registry and enabling efficient deployment strategies. When working with Docker Hub, always include your username in the tag to ensure proper routing to your repository. In enterprise environments, you might be working with private registries, which require slightly different tagging conventions. A robust tagging strategy should include both version information and environment indicators. For example, you might use tags like prod v1.2.3 or staging latest. When working with local registries, ensure proper SSL configuration for secure communication. Remember that the latest tag, while convenient, can be dangerous in production environments as it makes it difficult to track which version is actually deployed. Consider implementing a tag retention policy to prevent your registry from becoming cluttered with old images. Pushing images to a registry is a critical step in the deployment pipeline. When pushing to Docker Hub or any other registry, ensure you have proper authentication configured. In production environments, use access tokens rather than password authentication, and regularly rotate these credentials. Consider implementing retry logic in your CZD pipelines for push operations, as network issues can sometimes cause pushes to fail. For large images, consider using compressed layers and implementing parallel push operations where supported. When pushing to private registries, ensure proper network access and firewall configurations. It's also important to implement proper logging and monitoring for push operations to quickly identify any issues in your deployment pipeline. Pulling images from a registry requires careful consideration of several factors. First, implement proper image pull policies in your deployment configurations. In Kubernetes, for example, you might use always for development environments, but if not present, in production to prevent unnecessary downloads. Consider implementing image pull secrets securely, especially in orchestrated environments. Rate limiting can be an issue with public registries. Consider implementing a pull through cache or mirror registry for frequently used images. When pulling images in production, always verify image signatures and scan for vulnerabilities before deployment. Remember to implement proper error handling for cases where pulls fail due to network issues or registry unavailability. These fundamental Docker commands form the backbone of container operations. The Docker run command is particularly powerful. Beyond basic container creation, it supports numerous options for network configuration, resource limits, and volume mounting. When using Docker exec for debugging, remember that this should be a temporary measure. Persistent changes should be made through proper image updates. The Docker ps command is essential for monitoring container state, but in production environments, you'll want more robust monitoring solutions like Prometheus and Grafana. Container cleanup through Docker stop and Docker rm is crucial for resource management, but implement proper checks to ensure you're not stopping critical services. Consider implementing automated cleanup policies for stopped containers to prevent resource exhaustion. These additional Docker commands are essential for maintaining a healthy container environment. The Docker images command helps manage your local image cache, but remember to implement regular cleanup of unused images to prevent disk space issues. When using Docker container prune, be cautious in production environments. Implement proper filters to avoid removing containers that might be temporarily stopped. The Docker logs command is crucial for troubleshooting, but in production, implement centralized logging solutions like Elk Stack or Splunk. The Docker inspect command provides detailed container metadata useful for debugging but also for automated health checking and monitoring. Consider writing scripts to parse inspect output for automated environment validation. Now we come to an exciting hands-on assignment that will help you apply everything we've learned about containerization. This exercise will walk you through deploying a complete web application using Docker. This isn't just a theoretical exercise. It's designed to mirror real-world deployment scenarios you'll encounter in your DevOps career. By completing this assignment, you'll gain practical experience with image building, registry management, and container deployment. Let's dive into the specific requirements and objectives. The objective of this assignment is to give you hands-on experience with the complete container deployment lifecycle. You'll be building and deploying a web application using Docker, which will reinforce the concepts we've covered in this module. This exercise is particularly valuable because it combines multiple aspects of containerization, from writing Docker files to pushing images to a registry and managing running containers. The skills you'll develop here are directly applicable to real-world scenarios, whether you're working in a startup or an enterprise environment. This assignment will also help you understand the importance of proper documentation and version control in container deployments. Before beginning this assignment, ensure you have Docker installed and running on your machine. This means having both the Docker daemon and client tools properly configured. While the requirements mention just Docker and a Docker Hub account, I recommend also having a code editor installed for working with configuration files. Take time to properly set up your Docker Hub account. You'll be using it extensively. If you're working in a corporate environment, ensure you have the necessary permissions to pull and push images. Consider setting up a personal access token for Docker Hub authentication, rather than using your password directly. This is a security best practice that you'll want to follow in real-world scenarios. The first set of tasks focuses on setting up your application environment. When creating your project directory, consider implementing proper version control from the start. Initialize a Git repository and create a gitignore file. The HTML content provided is minimal, but feel free to expand it to include more complex features like CSS styling or JavaScript functionality. When creating your Docker file, consider the security implications of using the latest Nginx image in production. You'd want to specify a particular version. The file structure we're creating here mirrors common web application layouts, making it easier to expand the application in the future. Remember to follow proper naming conventions and directory structure. These habits will serve you well in larger projects. Building and tagging your Docker image are crucial steps in the container lifecycle. When building your image, pay attention to the build context. Ensure you're not including unnecessary files that could bloat your image size. The tagging convention shown here uses the latest tag, but consider implementing semantic versioning for better version control. Remember that each build creates a new image layer. Optimize your Docker file to minimize the number of layers and reduce the final image size. When pushing to Docker Hub, ensure you're using secure credentials and consider implementing automated build and push processes through ECCD pipelines. These steps form the foundation of container image management in production environments. In this phase of our assignment, we focus on the crucial steps of pushing your container image to Docker Hub. The login process might seem straightforward, but it's essential to understand the security implications. In production environments, you'll want to use configuration files or environment variables to store credentials securely. When pushing images, consider implementing a robust tagging strategy that includes both version numbers and environment indicators. For example, you might use tags like prod v1.0 and staging v1.0 to clearly indicate the intended deployment environment. It's also important to implement proper error handling in your deployment scripts to manage cases where the push operation fails. Consider implementing retry logic and proper logging to troubleshoot any issues that might arise during the push process. The final phase of our assignment brings everything together as we deploy and verify our containerized application. When pulling your image for deployment, always verify the image integrity and scan for potential security vulnerabilities. The port mapping specified in the run command P8080 is crucial for accessibility, but in production environments, consider using reverse proxies and proper load balancing. The verification step using a web browser is important, but in production, you'd want to implement proper health checks and monitoring. Consider adding automated testing to verify the deployment, including integration tests and end-to-end testing. This assignment has given you a foundation in container deployment, but remember that in real-world scenarios, you'll need to consider additional factors like scaling, high availability, and disaster recovery. Take time to experiment with different configurations and explore advanced features like Docker Compose and container orchestration platforms like Kubernetes. We've covered a comprehensive range of containerization topics in this module, from basic Python applications to complex multi-container deployments with volume management. Now is your opportunity to ask questions about any aspects that need clarification. Whether you're curious about production deployment strategies, security best practices, or scaling considerations, I'm here to help. Remember that containerization is a vast field, and these examples are just the beginning of what's possible. Feel free to explore beyond these examples and experiment with different configurations and deployment scenarios.